Hi, everyone. My name is Luis. I'm a lecturer at the School of Applied Mathematics at the Getúlio Vargas Foundation in Brazil. And this is joint work with Renko Buka, who is a researcher at the University of Auckland. And today I'm going to be talking about SBC, simulation-based calibration for phylogenetics. And what I hope to convey is what I call phylogenetic exceptionalism, meaning I'm going to try and show you that phylogenetics is a very special problem that requires that we think about certain things in a different way. All right, so phylogenetics depends fundamentally, of course, on trees, phylogenetic trees, and these trees are hypotheses about the world. They are graphs that describe hypotheses about evolutionary history, right? So hopefully you know by now that the correct hypothesis about the evolutionary history of humans, chimps, and gorillas is this middle tree here, right? So we might be inclined to think that whatever chimps and gorillas are more closely related because they are furry and, you know, or whatever, but no, actually humans and chimps diverged around about 5 million years ago, and the gorillas and the ancestor of chimps and humans diverged around about 8 million years ago. So hopefully you have noticed by now that I'm using this tree to tell a story, right? So I'm telling a story about how evolution went, right? Good. So these trees are hypotheses about the data, and of course, then we can use data to test these hypotheses and understand which of these are credible and which aren't, right? So in the case of this particular problem, we know with, you know, beyond the shadow of a doubt that this is the correct evolutionary history because we have a lot of evidence. The other thing that we can do with trees, which is slightly different from what I've shown, is we can, so if you imagine there's a an arrow of time here going downwards, this is a population that's not growing or decreasing, it's stable through time, and this is an exponentially growing population. And what I'm showing here is a process whereby we sample these red individuals, right, through time. And what we're doing here is we are tracking the ancestry between all of the red individuals. So the yellow dots here depict ancestors, unsampled ancestors, and the red dots show sampled individuals. And what's important to notice from both these trees is that the temporal sampling process imposes constraints on the tree, right? So the ancestor of these three individuals here cannot possibly live here, right? Because, you know, there's a temporal precedence constraint on this tree, and that will complicate things when we try to estimate phylogenetic trees from data coming from these red individuals, right? So there will be some structure that imposes additional constraints on tree space. And as you can see, different population dynamics will lead to different tree shapes. Hopefully that will be clearer in the next slide. So why do we care about trees? Well, there are two answers, right? The first is that we care about the actual tree because it tells a story about evolution, and we might be interested in that particular story, right? But even if you're not interested in the tree, you might be interested in making inferences conditional on the tree, right? So for instance, you can infer things about population dynamics from tree shape, and you can also infer things about migration and other processes from the clustering pattern of certain traits on the tree, right? So that means you really want to properly account for the uncertainty on the trees, so you can make principled inferences about the other parameters or the other processes that you do care about. Right, so one major difference between phylogenetics as a statistical problem and most other statistical problems out there is that we can usually always find some mapping from the space of parameters, the parameter space, to a manifold, right? To RD for D, suitable D. But for trees, this is not true. It's not true at all. We can actually prove that there's no embedding of tree space onto RD for any D. So we need to be a bit clever about how we represent tree space, and some representations will be better than others. So what I'm showing here is a sort of metagraph representation of tree space, in which each vertex is a tree, and we connect these trees if they are a certain distance from one another. In particular, in this case, we're defining what we call the SPR distance. So SPR stands for subtree, prune, and regraft. So an SPR operation is I take a subtree, let's say 1 and 3 here, right? This is a subtree. I take it, I prune it, so I cut it off, and then I glue it somewhere else in the tree, turning the original tree into another one, right? And if I can turn A into B with just the one SPR operation, then they are connected in the SPR graph. And of course, if I can't, then they aren't, right? So we know a bunch of things about this graph, and it makes it easier to think about stochastic processes in the space of trees. This is just an illustration of how the sort of hoops we need to jump through to try and represent tree space in a meaningful way. Right. The next thing I would like to mention is what the target posterior distribution looks like for a phylogenetic problem, right? So little t here stands for the branching order, which in phylogenetics we confusingly call topology. Where, mathematicians in the audience will know that topology means something slightly different, but we usually say this is the tree topology. B here is a vector of fixed size that depends on the number of leaves, and that's the branch lengths. So we have a tree, the branching order, and also what the lengths of the individual branches are. And omega here are the parameters, other parameters that we care about, like mutation rate and migration rate and population size, all of those parameters that we might be interested in scientifically that depend on the tree somehow, right? Depend on the tree structure. And I'm well aware that we usually don't have to write the normalizing constant for our target, but the reason I wrote it down here is that we can sort of understand the difficulty, the complexity of the problem. So to obtain this normalizing constant, you would have to marginalize over the branch lengths, and that's linear in the number of leaves. Then you would have to integrate over omega, so all of those parameters, which can be really high dimensional. And then once you've done that, all you need to do is repeat that integration process for every tree in tree space. So to give you an idea of how big that space is, if you had 53, around about 53 leaves in your tree, which is not a big data set at all these days, you would have more possible trees than there are atoms in the observable universe. So something bigger than 10 to the 80. So this is an absolutely ginormous space full of terraces and flat regions. It's really hard to explore. Right. So how do we do SBC for trees then? Well, one thing we can do, and this is the solution that Remco and I came up with, is we are going to map trees to something that's on, say, the real line, and then we're going to compute ranks on that space. So to do that, what we do is we pick an anchor or focal tree, tau naught. And in this particular case, we're picking it from the prior. And then we proceed sort of normally as you would in SBC. So we draw trees from the prior, and then we compute the true distance from that tree to the anchor tree. Then we generate some data from the conditional distribution of the data and the tree. And then with that simulated data, we compute, approximately compute the posterior, and we look at the distances of each posterior sample to tau naught, our anchor tree. And then finally, we look at the ranks, right? So what we're doing here is we're projecting things in tree space to quote unquote distance space. And then in that space, because that space has well ordering, we can compute ranks, right? So that's what we do there. Right. So here I'm showing you some very preliminary results, and the results are really not important here. What's important is the discussion that will hopefully ensue from this. So I'm looking at Robson-Folt's distance. So here on the panels, we have two different methods, two different samplers. So this is state of the art. This is something that I've developed during my PhD. And here we're looking at Robson-Folt's distance, which only takes differences between branching orders into account. So it ignores branch lengths. And we're also looking at the same set of experiments, right? But using BHV distances. So BHV stands for Bilera, Voigtman, and Holmes. That's a slightly complicated distance that does take branching order and branch lengths into account. So it takes the whole tree into account to compute distances. And what we see here, which is slightly worrying, and that's something that I want to share with you, is that if you look at this particular distance, you don't see any problems for either sampler. But if you look at this distance, BHV distance, then you do detect some weirdness that you would obviously want to investigate further, right? So I guess the conclusion from this set of experiments is that if you want to do SVC for trees, one thing you can do is map to a distance space. But then if you do that, nothing guarantees, that distances, that every distance will give you the same set of diagnostics. So, you know, certain distances will highlight problems, whereas others won't. And that's slightly worrying. We can also do this for continuous parameters. So the omega there that I talked about. So this is population size. This is some phylogenetic some, mutation stuff, the frequency of each nucleotide or whatever. This comes from Remco's application. So this is something that we are kind of developing and sort of mirroring the stuff that's being developed in the SBC package. So you can look at these two things. You can look at the histograms, let's say, for the tree distances, and you can also look at that for omega as you would for any other model, right? So I would like to spend a couple minutes on this last slide, because I think that's quite informative to people that are not familiar with phylogenetics. So first of all, as I hope to have conveyed, the parameter space is humongous, right? And very complicated because the branch lengths interact with the tree topology in a known standard way. And it's also very big. And importantly, these runs take days at a minimum, right? So we're not talking about things that you can do in a couple minutes in Stan. We're talking about things that take days to run, right? So what we need is early stopping. So this is something that's an idea that I would like to put out there, that we need to think about SBC in sort of a step-by-step way, whereas you do a few simulations and you try to detect gross problems so you can stop early and not waste a lot of computation power to discover in the end that your sampler is bad and your model is not well calibrated for that sampler. The other difficulty that I would like to mention is that because the parameter space is very non-standard, there's no way to do a single proposal that updates all of the parameters at once, as you do in Stan, right? So in Stan, what you do is you write down your model, Stan maps that to Rn, does HMC in there, and then maps back, right? That cannot be done in phylogenetics, at least not easily. So what we usually do is we have a set of proposals for omega, we have a set of proposals for T and for B, for the tree topology and branch lengths. And having multiple proposals means there are other knobs they need to turn in order to calibrate your sampler, right? So there's no, in Stan, if Stan works, then it works, right? Because it has a single proposal. But if in other phylogenetic software, if it doesn't work, you can never know if it's because one of the proposals is messed up or because something else deeper, some deeper problem is at play here. So I hope to have conveyed these special features of phylogenetics and probably give you food for thought. So with that, thank you very much. I'll see you in the live Q&A session. Bye.